So those are the cases, and you can work through this in detail to make sure you understand it. So I'm not going to do that. There is a theorem here, 8.1, which you can go through about solving matrix equations. And in order to give you an understanding, I'm going to do something with notation that will help you understand what's going on. If I have a scalar equation and I say ax equals b, how do I solve that equation? What do? I divide by a. Okay, now I'm not going to say I divide by a, because division is something that only makes sense in arithmetic where you have scalar values. I multiply by the reciprocal, but in this case I call it the inverse. Okay, same thing. I'm going to multiply by the inverse. So the inverse of a, which is written as a to the minus 1, is equal to 1 over a in one dimension. Now if I write this in If I write an equation like this in scalar notation, in matrix notation, and I say that this is n by n, and this is n rows by one column, then that'll set up n equations in n unknowns. So you can see we've done it in 2 dimensions. But this is why I say matrix theory is very powerful, because it applies to, I can write down 3 equations in 3 unknowns, 4 equations in 4 unknowns. They're all represented by the same notation. In mathematics is about getting the right notation, because if you have the right notation, and then you can manipulate the symbols in ways that are meaningful. So in order to really solve mathematical problems, you have to be able to get the right structures for describing things. Now, the Romans couldn't do arithmetic very well. Why couldn't they do arithmetic very well? Yeah, they had a horrible way of representing numbers. They didn't have the concept of a base. We use base 10. Now, you can have different bases. So base 2 is very highly utilized today. You know what? It's called the binary system. So where's it used? Computers. Because computers only know on-off. They don't know 1 to up to 10. So they work in things either 1 or 0. But we work 10. So in order to do arithmetic, you had to get a way to represent numbers. So that multiplication was very simple. Roman numeral multiplication is horrendous. Multiplication in a system where you have bases is very simple. It's the same thing here. Solving equations can be horrendous unless you've got the right notation. So we're going to say, if there's something that I can call the inverse of a, and I'll call it a to the minus 1, then what do I mean by solving this equation? Well, over here, I take a to the minus 1 times a is equal to a to the minus 1 times b. So I pre-multiply by a to the minus 1. Now, what is a to the minus 1 times a? That's 1. So that means, sorry, I left out the x here. So I take about ax, I'll pre-multiply by a to the minus 1. So here I get 1 times x is equal to a to the minus 1b, and 1 times x is just x. So x is equal to a to the minus 1 times b. In the same way, what I'm going to do is I'm going to take this equation and pre-multiply it by a to the minus 1. Now, that somehow has got to be equal to an object that when I multiply it by x gives me x. And I call this object the identity matrix. And the identity matrix is a matrix that looks like this. If I take the matrix 1, 0, I'll do this in 3 dimensions, 0, 1, 0, 0, 0, 1, and I take a vector x1, x2, x3, then in order to, this is a 3 by 1, sorry, a 3 by 3, multiplied by 3 by 1, so I expect to get something that's 3 by 1, 3 by 1, okay? So 1 times x1 is x1 plus 0 times x2 plus 0 times x3, so I just get an x1. 0 times x1 is 0, 1 times x2 is x2, 0 times x3 is 0. 0 times x1 is 0, 0 times x2 is 0, 1 times x3 is x3. So I call this the identity matrix in 3 dimensions. So in other words, if I take a matrix A, if I can find another matrix, which I'll call the inverse of A, that I pre-multiply A by, and that gives me the identity matrix, then I have been able to solve this problem just by finding the inverse of A. So in order to solve this equation, it comes down to finding the inverse of A. Now what happens is, I can find the inverse of A provided the determinant of A is not 0. So in 1 dimension, I cannot do this if A is 0, provided A is not equal to 0. In 2 dimensions, I cannot do this if the determinant of A is 0. So firstly, all the elements of A cannot be 0, and if some of the elements of A are non-zero, I have to make sure that the determinant of A is not 0. And if that is true, then I can solve this equation. And so, if I go through this process, I can show that this equation over here that I wrote down in this form, I kind of go through the mechanics of this, I can show that the inverse of A is a matrix that looks like this. And how can I tell that that's true? Let me write that down and we'll do the multiplication and we'll see. So I have a matrix A equals A, B, C, D. And now I have a claim by this theorem that there's a matrix called A to the minus 1, which is 1 over, now this 1 over A, D minus BC is a scalar value outside. And then I have the matrix D minus B minus CA. D minus B minus CA. And you can see what happened. I've swapped A and D to be D and A, and then I've taken the B and put a minus sign in front of it, and I've taken the C and put a minus sign in front of it. And then I've written down 1 over the determinant. So that's A to the minus 1. So this is provided that AB is not, sorry, AD is not equal to BC, which is the same as saying the determinant of A is not equal to 0. And when I do this multiplication, let's do a to the minus 1 times A, and that is equal to 1 over AD minus BC, D minus B minus C, A, and then I'm multiplying that by A, B, C, D. So that's equal to 1 over AD minus BC. Now the first term here is A times D plus minus B times C. So you see it's exactly the same as this. I've got this number divided by this, which gives me a 1. The second one is going to be AB, A times B, and then minus B times D. Sorry, this is a D. Looks like an A. So it's AD, A times D, minus B times D. That's not right. D minus B, dB, minus BD, yeah. Sorry, it's D times B, minus B times D. So that's 0. So this turns out to be the same as this, and this turns out to be 0. So what's going to happen is we'll get the same thing over here, minus C times A, and then plus A times C. So this turns out to be 0. This turns out to be 0. And now we're going to get minus C times B, plus A times D. And this thing is the same as that. So when I divide this into this, and that's 0 and 0, and I divide this into this, then this is equal to 1, 0, 0, 1. Okay? So that is the identity matrix. So we found a matrix. So that means if you want to solve these linear equations, if you've got a matrix A, B, C, D, all you can do is write down this matrix A to the minus 1, and then multiply it by the vector on the right-hand side, and you've got your solution. So there's a set of examples here that you can go through to check that out. Okay, so that's, I'm not going to do any more to do with matrix multiplication and finding inverses. So you need to read through the textbook and your notes and whatever, and make sure you understand that stuff, okay? Because I want to get on with the application, which is using these kinds of ideas to build and understand models. Okay, thanks.